history, and overview of ClojureScript. ClojureScript is a variant of the Clojure language which compiles to JavaScript. It was created by Rich Hickey and first released in 2011 to leverage the capabilities of the JavaScript engines in modern browsers, while bringing the power and expressiveness of Clojure to front-end development. This code demonstrates a basic ClojureScript expression to output the string "Hello ClojureScript" to the console. The println function is a standard Clojure and ClojureScript function used printing output. Setting up the development environment. Before we can start writing ClojureScript, we need to set up a development environment that can compile ClojureScript code to JavaScript. This typically includes installing Java, Clojure, and Node.js. We'll use LineEngine, a popular Clojure build tool, to manage our project. First, we install LineEngine using Homebrew, replace with appropriate package manager for your OS. Then we create a new project called My Project, using the line new command with the Figwheel template, including the reagent library for React integration. CD is used to change the working directory to My Project. To get started with live coding, we run line Figwheel, which starts a local development server and opens the app in a web browser with hot reloading enabled for a smooth development experience. Difference between Clojure and ClojureScript. Clojure and ClojureScript are two dialects of the same language designed for different runtime environments. Clojure targets the Java Virtual Machine, JVM, while ClojureScript compiles to JavaScript and is primarily intended for web development. Let's look at a code example that emphasizes a key difference: ClojureScript's interop with JavaScript. In this code snippet, JS is ClojureScript's namespace for JavaScript interop. It allows ClojureScript to call JavaScript functions directly. In this case, alert is a JavaScript function being called from ClojureScript to display a message box in a web browser. This kind of interop is specific to ClojureScript and has no direct equivalent in Clojure, as Clojure interacts with Java, not JavaScript. Basic syntax and semantics. ClojureScript, like Clojure, uses a Lisp-based syntax where data structures and code share the same form. Here we will look at the representations for basic literals, such as numbers, strings, booleans, and nil. The code defines a vector containing different types of literals. The number 1 represents an integer, the string 2 is enclosed with double quotes, true is a boolean value, and nil represents the absence of a value. The read-eval-print loop, REPL. The REPL is an interactive environment where you can write and evaluate ClojureScript code in real time. This tool provides a dynamic programming experience, allowing for immediate feedback and experimentation. Upon entering the line of code in the REPL and pressing enter, the REPL reads the code, evaluates it, executes, and prints the output, which is "Hello ClojureScript." It then returns to a new line, ready for more input. Literals. Strings, numbers, characters, booleans. In ClojureScript, literals are notations for representing fixed values directly in the code. They are used to create values of different types, such as strings, numbers, characters, and booleans, without having to define them first. Let's look at how these literals are used in ClojureScript. The code defines 4 different literals in ClojureScript. Example string is a string literal enclosed in double quotes, representing a sequence of characters. Example-number is a numeric literal, which in this case is an integer. Example character is a character literal, denoted by a backslash followed by the character. Example boolean is a boolean literal, which can be either true or false, representing a truthy or falsy value respectively. Naming conventions and defining variables. In ClojureScript, as in many programming languages, adhering to common naming conventions is important for code readability and maintainability. Names should be descriptive, using lowercase and separating words by hyphens. In the code snippet, my first variable is a variable holding a numeric value, another value holds a string, and calculate sum is a function definition. The use of hyphens to separate words is a ClojureScript convention, distinguishing it from camel case, typically used in JavaScript. Collections, lists, vectors, maps, sets. In ClojureScript, collections are a fundamental concept, providing a way to store and manipulate groups of values. There are 4 primary collection types: lists, vectors, maps, and sets. Each has its own structure and use cases. Lists are linked lists, vectors are resizable arrays, maps are key value pairs, and sets are collections of unique elements. In the code snippet, MyList is defined as a list containing the elements 1, 2, and 3. Lists are good for sequential access and are created using parentheses. MyVector is a vector that allows indexed access, created with square brackets. MyMap is a map with keys A, B, and C, and their corresponding values 1, 2, and 3, declared using curly braces with colons denoting the keys. Finally, MySet is a set that holds unique elements without any particular order and is defined using curly braces prefixed with a hash sign. Control structures if, do, when, loop recur. The if construct in ClojureScript is used for conditional execution. It evaluates a condition and, based on whether the condition is truthy or falsy, it evaluates one of the two expressions provided. In this example, if the variable x is greater than 10, it will print x is greater than 10. If x is not greater than 10, it prints x is not greater than 10. Anonymous functions and higher order functions. Anonymous functions in ClojureScript are functions that are not bound to an identifier. They are useful for short, on-the-spot functionalities and are also referred to as lambda functions. They can be created using the fn keyword or the shorthand syntax haha. The code uses an anonymous function, stenta2, to double each element in the vector 1, 2, 3, 4, 5. The cent symbol is a placeholder for each element passed into the anonymous function. This function is then applied to each element using map, which results in a new sequence where each number is doubled. 2, 4, 6, 8. Destructuring. In ClojureScript, destructuring allows you to bind names to values inside of collections directly within the binding form. This can be used with vectors, maps, sets, and even nested structures to make extraction of data straightforward without needing to manually access each item or property. In the first code snippet, a vector 1, 2, 3 is being destructured, and each item is bound to a variable, A, B, and C, sequentially. Thus, A equals 1, B equals 2, and C equals 3. The println function then outputs these values. In the second snippet, a map x10, y20 is destructured. The keys x and y from the map are associated with the variables x and y correspondingly using the keys shortcut, and then printed out. This simplifies the process of extracting multiple pieces of data from collections. Defining functions. In ClojureScript, functions are first-class citizens, which means they can be used just like other types of values, e.g. numbers, strings. Functions are defined using the fn keyword or the defn macro, which is a shorthand for defining a named function. Here's how to define a simple function. In this code, defn is used to define a function named greet that takes one argument, name. The function body uses star to concatenate hello with the provided name and an exclamation mark to create a greeting. The function is then called with the argument world, resulting in the string hello world. Arity overloading. Arity overloading in ClojureScript allows a function to have different behaviors based on the number of arguments, arity, passed to it. This is particularly useful for defining flexible interfaces to functions. In the provided code, the greet function is defined with two arities. The zero arity version calls the single arity version with a default argument, world. When greet is called without arguments, it prints hello world. When it is called with one argument, it prints a personalized greeting such as hello Alice. Closure properties of functions. In ClojureScript, as in other Lisp dialects, functions can create closures. A closure is a function that captures the bindings of free variables in its lexical scope. This allows the function to access those variables even when it is invoked outside of its original scope. In the provided code, makeAdder is a higher-order function that takes an argument x and returns a new function. The returned function takes an argument y and adds it to x, effectively creating an adder function specific to the value of x. When we call makeAdder5, we create a closure with x bound to 5. This is stored in add5. Calling add510 then adds 10 to 5, utilizing the closure property to remember the environment in which add5 was created. Recursion and tail call optimization. Recursion is a fundamental concept in functional programming where a function calls itself to solve a problem. In ClojureScript, recursion allows functions to operate on complex data structures by breaking them down into simpler parts. This is a recursive function for calculating the factorial of a number. If n is 0, it returns 1. Otherwise, it multiplies n by the factorial of n minus 1. Each call to factorial waits for the result of a recursive call, creating a new stack frame. Macro basics. In ClojureScript, macros are a powerful aspect of the language that allow developers to effectively extend the syntax of the language itself. Macros perform transformations on the code at compile time, which means they are a way to generate code using code. The def macro form is used to define a new macro called myMacro, which, when called, will expand to a println function call that outputs a string. The backtick indicates syntax quoting, which is used to return the following form as is, unless unquoted with Golsh. No actual function call or printing happens during macro definition. When myMacro is used in code, at compile time it will be replaced with the body of the macro. Writing custom macros. Macros in ClojureScript allow you to write code that manipulates code, enabling metaprogramming. They are compile-time constructs that receive code as input and produce code as output. Writing a custom macro involves understanding how to handle syntactic forms and how to generate code that performs the desired operations at compile time. In this example, def macro is used to define a new macro called sayHello that takes one argument, name. The syntax quote, backtick, is used to specify a template for the code that should be generated when the macro is expanded. The tilde, sha, is the unquote operator, which replaces the name with the actual argument passed during macro invocation. When the sayHello world is called, it gets expanded at compile time into println hello world. Persistent data structures. In ClojureScript, persistent data structures provide a means to work with immutable data. When you modify a persistent structure, the original remains unchanged and a new version with the changes is returned. Under the hood, ClojureScript data structures use structural sharing to make these updates efficient. Here, myVector is a vector containing the elements 1, 2, and 3. When we conjure a new element 4 to myVector, it does not modify the original vector. Instead, newVector is a new vector that contains 1, 2, 3, and 4. The println function calls show that myVector retains its original form, demonstrating immutability. This is possible due to the persistent nature of ClojureScript data structures. Sequence abstractions. In ClojureScript, sequence abstractions are a core part of the language. They allow you to work with collections of data in a consistent way, regardless of the specific type of the underlying data structure. Sequence functions can operate on lists, vectors, sets, and even strings and maps by viewing them as sequences. Here's an example of sequence manipulation using the map function. The map function takes two arguments, a function and a collection. It applies the given function, inc in this case, which increments a number by 1, to each item in the collection sequentially. The collection 1, 2, 3, 4 is implicitly converted into a sequence, and inc is applied to each number, resulting in a new sequence, 2, 3, 4, 5. Lazy sequences. In ClojureScript, lazy sequences are collections whose elements aren't computed until they are needed, which can be very efficient when dealing with large or potentially infinite datasets. Instead of computing all the elements at once, ClojureScript computes elements one at a time in a just-in-time fashion as they are accessed. In the provided code, fibseek is a function that returns an infinite lazy sequence of Fibonacci numbers. It uses iterate to infinitely apply a function that generates the next Fibonacci number from the previous two. This sequence is lazy because the next number is only calculated when needed. Take is then used to extract only the first 10 numbers from the sequence, demonstrating how to work with potentially infinite sequences without calculating all the elements. Transducers. Transducers are composable algorithmic transformations. They are independent of the context of their input and output sources, and specify only the essence of the transformation in terms of an individual element. This makes them particularly flexible and powerful for building complex data processing pipelines without being tied to specific collections. In this example, XF defines a transducer composed of two operations, filtering odd numbers, and then incrementing each filtered number. The comp function is used to compose the two transformations. Transduce applies the transducer XF to each element of the range of numbers from 0 to 9, using plus as the reducing function and 0 as the initial value. The result is a sum of all odd numbers after being incremented from the given range. Protocols and records. In ClojureScript, protocols are a way to define a set of functions that can be implemented by different types. They are similar to interfaces in other languages and provide a method of polymorphism. Records are a data structure that implement one or more protocols. They are similar to classes in other languages, but with an emphasis on immutability. This code defines a protocol called iPerson with two functions, say hello and say goodbye. It then defines a record person that implements the iPerson protocol with concrete function definitions for say hello and say goodbye. Lastly, it creates an instance of person with the name Alice and calls both functions, which print greetings to the console using the name provided in the record. Immutability in ClojureScript. Immutability is a core concept in ClojureScript where data structures are immutable. This means that once a data structure is created, it cannot be changed or mutated. Instead, any operation that would traditionally change a data structure creates a new version of it. This approach simplifies reasoning about the state of your program and avoids many common pitfalls in software development, like unintended side effects. In the code, we define a map, myMap, with a single key-value pair. When we want to add another key-value pair to the map, we use the assoc function, which creates a new map, newMap, with the additional pair. myMap remains unaffected, demonstrating immutability. It cannot be changed after its creation. Atoms. In ClojureScript, an atom is a reference type that provides a way to manage mutable state. An atom holds a value and allows that value to be updated in a thread-safe manner, ensuring that changes are visible across threads. Atoms are commonly used when you need a simple way to update some shared state from various parts of your application. This code defines an atom, myAtom, with an initial value of 0 using the atom function. Swap is then used to apply the increment function to the current value of the atom, which updates the value to 1. The @ symbol is used to dereference the atom, i.e., to get its current value. As a result of dereferencing myAtom after the swap operation, we get the updated value, which is 1. Refs. In ClojureScript, refs are used to manage state that needs to be coordinated across multiple parts of an application. They provide a way to create mutable reference types that can be safely modified within the context of software transactional memory (STM). This allows changes to occur in a transactional manner, where updates can either all succeed or all fail, providing a powerful tool for concurrency control. In this code snippet, we define a ref R with an initial value of 0. The dosync block is used to ensure that all changes to R within it are transactional. Within the dosync block, we increment the value of R twice using the alter function, and finally, we dereference R with the @ operator to get its current value. If the dosync block is successful, the final value of R will be 2. If not, STM will automatically retry the transaction until it succeeds. Agents. In ClojureScript, agents are used for managing state changes. They allow for an asynchronous and independent state that can be updated using functions. When an agent's state is modified through these functions, the changes are done off the regular thread of execution, ensuring that your main program flow is not blocked. In this example, myAgent is created with an initial state of 0. The send function then asynchronously applies the inc function, increment, to the state of the agent. The deref, or its reader macro @ is used to get the current state of the agent. Since send is asynchronous, if you deref immediately after, you might get the old state before the update happens, depending on the timing of the agent's action. Vars and environment. In ClojureScript, vars are a fundamental concept for managing mutable state within the language's environment. A var is a container that holds a value and can be dynamically rebound to different values within different scopes, providing a controlled mechanism for managing state changes. The code first defines a dynamic var called myvar with an initial value of 10. The binding form is then used to temporarily rebind myvar to the value of 20 within the scope of the binding block. When println is called within the block, it outputs 20, the rebound value. Outside the binding block, println is called again and outputs 10, which is the original value of myvar, demonstrating that the rebinding was indeed temporary and localized to the binding scope. Accessing JavaScript objects and properties. In ClojureScript, interacting with JavaScript objects is a common task. You can directly access properties of JavaScript objects using the agit and aset functions, as well as the ... notation. It's essential to remember that ClojureScript property access follows the same rules as JavaScript regarding what characters are valid in property names. Here's an example of accessing JavaScript object properties in ClojureScript. The code sample defines a JavaScript object, JS_object, with two properties A and B. It demonstrates two ways to access these properties. The first method uses the ... notation to directly access the statically known A property. The second method employs ag to access the property named B, which is useful especially when the property name is dynamic or not valid as an identifier in ClojureScript, e.g., contains special characters or starts with a number. Calling JavaScript functions. In ClojureScript, you can call global JavaScript functions directly by using their names. For example, to use the alert function to display a message to the user, you can call it with the JS prefix followed by the function name. The code shows how to call the JavaScript alert function from ClojureScript. The JS namespace prefix indicates that the function is a member of the global JavaScript environment. This functionality allows ClojureScript to interact with the global functions provided by the host environment. Using JavaScript libraries. ClojureScript allows seamless use of JavaScript libraries, enabling access to the wide ecosystem of JavaScript. This is done via the JS namespace or through require, with as and refer in the namespace declaration. In this example, we demonstrate how to use the jQuery library in a ClojureScript project. We first require the jQuery library and alias it as $, similar to how it's typically used in JavaScript. We then make an AJAX request to a URL using jQuery's AJAX method. Here we're just logging the result for simplicity. To work, jQuery should either be globally available in the runtime or appropriately bundled with the ClojureScript project using a module bundler or a similar tool. Working with JSON. In ClojureScript, JSON manipulation is common when dealing with web APIs or JavaScript libraries. You can convert ClojureScript data structures to JSON and pass JSON into ClojureScript data structures using the cljs.core library, which is a part of the standard ClojureScript API. The functions clj.js and jsclj are used for these conversions. The code sample begins by requiring the cljs.core library, which contains the clj.js and jsclj functions needed for JSON interop. It defines a ClojureScript map CLJ data and converts it to a JavaScript object, JSON, using clj.js. The resulting JavaScript object is assigned to JSON data. It then shows the reverse process, where the JavaScript object JSON data is converted back into a ClojureScript map using JSCLJ, resulting in CLJ map. These conversions are essential for passing data between ClojureScript and JavaScript code. The Google Closure Library and Compiler. The Google Closure Library is a robust modular library of JavaScript code that can be used in developing large, complex web applications. It provides cross-browser functions for DOM manipulation, events, and more. The Closure Compiler is a tool for making JavaScript download and run faster by optimizing the code. It compacts the code, removing dead code and rewrites and minimizes what's left. In this ClojureScript snippet, we define a function getElementById that takes an ID as an argument. Inside the function, we're using goog.dom/getElement, which is a function from the Google Closure library that retrieves an element by its DOM ID. ClojureScript is designed to work seamlessly with the Closure library, enabling the use of its functions directly within ClojureScript code. The compiler will then optimize this during compilation. LineEngine and boot setup. LineEngine is a build automation and project management tool for Clojure. It's used to automate tasks such as compiling code, running tests, and managing dependencies. To set up a ClojureScript project using LineEngine, you would typically start by installing LineEngine and then creating a new project or configuring an existing one. The provided code features two parts, a command line statement and the content of a project.clj file. The line new cljs hello world command initializes a new LineEngine project with the name cljs hello world. The project.clj file defines the project configuration, including the project dependencies, Clojure and ClojureScript, the plugin line.cljs build for compiling ClojureScript, and a clj build configuration that specifies a build with development settings, an entry point, cljs hello world.core, and the output files, out main.js out directory. Shadow CLJS, an advanced build configuration. Shadow CLJS is a build tool for ClojureScript that aims to make it easier to work with JavaScript ecosystems by simplifying the configuration, integration, and development workflows. It provides advanced build configurations, which involve specifying various compiler options, modules, and optimizations tailored for different environments and use cases. In the provided shadowcljs.edn file snippet, we've specified key build configurations for a ClojureScript project. Source paths contains paths to the source files. Dependencies lists required libraries with their versions. Under builds, we define a build with the app key targeting a browser environment. Output dir and asset path customize where compiled files will be placed and how they'll be referenced. Modules defines code splitting with main module initializing the app through myapp.core/init. DevTools specifies development time tools with the afterload hook. Here it calls myapp.core/reload after code changes. Source maps and debugging. In ClojureScript, source maps are an essential feature for debugging. They provide a way to map the compiled JavaScript back to the original ClojureScript code. This helps developers understand and debug their code in the context of the original source, as opposed to the transformed and often minified output JavaScript. In the provided compiler options, source map true is a setting which tells the ClojureScript compiler to generate source maps along with the compiled JavaScript files. When an error occurs, or while debugging, you can then see the relevant ClojureScript code instead of the less human-friendly compiled JavaScript. This feature is usually configured within your project.clj for LineEngine or in the shadowcljs.edn file, depending on your build tool. Optimizations and code splitting. In ClojureScript, compiler optimizations are crucial for reducing the size of the compiled JavaScript, improving load times, and enhancing performance. Three primary optimization levels exist: none, simple, and advanced. This snippet from a LineEngine project.clj or build.cljs file configures the ClojureScript compiler to use advanced optimizations, which includes aggressive code minification and dead code elimination. It also disables PrettyPrint to reduce file size. Working with NPM and Node.js. ClojureScript can interoperate with the extensive ecosystem of JavaScript libraries available via NPM, and it can run on Node.js as well as in the browser. Using NPM packages within a ClojureScript project involves configuring your build tool to include and manage these external dependencies. The code snippet shows a dep.cljs file that specifies NPM dependencies for a ClojureScript project. It declares a dependency on React and React DOM, specifying the versions to use. The install deps true flag tells the ClojureScript compiler to automatically install these NPM dependencies when compiling the project. This feature enables ClojureScript developers to easily integrate JavaScript libraries directly from NPM into their workflow. Introduction to Reagent and React. Reagent is a minimalistic ClojureScript interface to Facebook's React library. Reagent provides a way to write React components using ClojureScript with a more concise syntax and functional flavor. It leverages React's virtual DOM for efficient updates and rendering. This code snippet demonstrates the definition of a simple Reagent component called Simple Component. It returns hiccup-like syntax which Reagent transpiles to React components. The literal vector, div, represents a div element with an h1 child containing the text, Hello Reagent. The render function is then used to mount this component onto the DOM element with the ID app, which is typical usage for a ClojureScript app interfacing with an HTML document. Creating components with Reagent. In Reagent, a ClojureScript interface to React, components can be created as simple functions that return hiccup syntax. These components can manage state, lifecycle methods, and utilize React features through the use of Reagent's Form 1, Form 2, and Form 3 component forms. Let's create a simple Reagent component as an example. Here we define a simple Reagent component called greeting_component that takes name as an argument. The component function returns hiccup syntax in the form of a vector, which begins with the div keyword, indicating a div element, followed by a string that forms a greeting message. Each element inside the vector corresponds to a child of the div in React. When this component is used, e.g., greeting component Alice, it will produce a div element with the text content, "Hello Alice." Component local state and lifecycle. In Reagent, components can maintain their local state that is isolated from the rest of the application. This state can be created and manipulated using the reagent.core/atom function. The lifecycle of a component refers to the various stages it goes through, such as mounting, updating, and unmounting. Reagent components support lifecycle methods that allow you to run code at specific points in a component's life. The code snippet defines a Reagent component, timer component, that uses a local state, seconds elapsed, which tracks the number of seconds since the component mounted. The state is created as a Reagent atom. The component didMount lifecycle method is defined to set up a JavaScript interval that increments the seconds elapsed state every second. The Reagent render function is responsible for rendering the component's UI, which displays the elapsed seconds. This demonstrates both local state management and use of a lifecycle method in Reagent. Using Reframe for state management. Reframe is a ClojureScript framework for building user interfaces. It is built on top of Reagent. One of Reframe's core concepts is centralized state management, where a single atom, typically called appdb, holds the entire state of your application. Changes to the state are made through events, which are processed by event handlers. Queries on the state are made through subscriptions, which are managed by subscription handlers. The example code defines a minimal Reframe application. It begins by requiring reframe.core. An event handler is registered with Reframe's reg_event_db for the event initialize, which takes the current database state db and initializes the count key to 0. A subscription handler is also registered with Reframe/regsub for the subscription count that looks up the count key in the db. Lastly, a counter component Reagent component is defined, subscribing to the count state, displaying it, and providing a button to reinitialize the count via the initialize event. Routing with Secretary or WriteIt. Secretary is a client-side routing library for ClojureScript, inspired by the Ruby gem Sinatra. It allows you to define routes in a declarative manner and maps them to functions that will manipulate the view. Secretary manipulates browser history using the HTML5 history API. The example code demonstrates how to define two simple routes with Secretary, a home page route and an about page route. The diffRoute macro is used to create these routes, which match the URL path and bind a function that renders the appropriate Reagent components into the DOM element with the ID app. When the URL changes to either / or /about, the respective functions are executed, rendering the home or about page. Writing unit tests with Clojure.test. In ClojureScript, Clojure.test is a namespace that comes with the core language and provides the basic utilities for writing unit tests. It includes macros for defining tests, defTest, declaring what should be true in a test, is, and grouping tests, testing. Below is an example of a simple test using Clojure.test. The ends declaration at the beginning sets up our testing namespace and requires the Clojure.test and the namespace with the functions we're testing. defTest defines a new test named aTest, and within that, testing provides a context or description of what is being tested. The is macro is used to assert the truth of expressions. Here, we're testing basic arithmetic assertions. Finally, runTests is called to execute all the defined tests. Integration testing. Integration testing is a level of software testing where individual units are combined and tested as a group. The purpose of this level of testing is to expose faults in the interaction between integrated units. In ClojureScript, integration tests are important for ensuring that components of the application work together as expected. These tests often involve simulating user interaction with the application or testing multiple functions as they work together. In this example, an integration test is defined using defTest. The test involves initializing two components that are expected to work together. Component A init initializes the first component, and component B init initializes the second component, possibly using the first component as an argument to simulate dependency injection. Component B action represents an action performed on the second component. The test asserts that performing the action with a test input yields the expected output, thus confirming that the two components integrate and work properly together. Functional testing with cljs.test. In ClojureScript, the cljs.test namespace provides a testing framework to perform unit and functional testing. Functional testing generally involves testing the behavior of your application, often simulating real user interactions and validating that outputs are correct. Here, we'll set up a simple functional test with cljs.test. We begin by declaring a namespace for our test and requiring the cljs.test namespace. A defTest macro is used to define a test function, test user interaction. The testing macro provides a textual context for the test. Inside the test, we assume that there is a function called simulateFormSubmission that mimics a user submitting a form with input, and we compare its return value with the expected output using the is macro. Finally, the runTests function is called to execute the test. Code organization and namespace management. In ClojureScript, managing namespaces is critical for keeping code organized and maintainable. Namespaces prevent naming conflicts and provide a structure to group related functions, variables, and macros. The ends macro is used to declare a namespace. The given code snippet demonstrates the declaration of a namespace myapp.core. It also shows how another namespace myapp.utils with an alias utils. This allows you to reference any public function or variable from myapp.utils as utils/function name within the myapp.core namespace. Performance monitoring and optimization. Performance monitoring and optimization in ClojureScript are essential for creating efficient and responsive applications. When it comes to monitoring, tools such as CS DevTools and Browser DevTools can help identify performance bottlenecks. Optimization often involves using immutable data structures wisely, avoiding unnecessary calculations, and leveraging advanced compilation modes. In the provided code, frequently called function is a function that might carry out an expensive operation. To optimize its performance, especially in the context of an event that fires often, such as an onChange event on an input field, it's wrapped in a debounce function with a 250 milliseconds delay. This ensures that the operation isn't called more than once every 250 milliseconds, thus preventing unnecessary work and improving performance. It's a simple yet powerful way to optimize functions that don't need to run continuously or can be slightly delayed without affecting user experience. Server-side rendering, SSR, with ClojureScript. Server-side rendering, SSR, with ClojureScript involves the process of rendering a web page on the server instead of in the browser. This allows the page to be fully rendered with content before being sent to the client, which can significantly improve load times and SEO. ClojureScript, being a language that compiles to JavaScript, can be used on the server with the help of Node.js, although this is less common compared to client-side scenarios. The code snippet defines a ClojureScript namespace for server-side rendering, requiring the cljs.node.js module for Node.js interaction and a hypothetical server-side rendering.page module for rendering. The render page to string function calls a render function with some initial content. The result is stored in the response and returned via node/return, which would send the HTML content back to the client in a Node.js environment. Working with web workers. Web workers allow for running JavaScript in background threads, enabling heavy processing without blocking the main thread and affecting the performance of a web page. In ClojureScript, interacting with web workers involves creating the worker instance, sending messages to the worker, and receiving messages from it, just as in plain JavaScript. In this ClojureScript code, we create a new web worker by initiating a JavaScript worker object with the path to our worker script. We then set up an event listener to handle message events, which are triggered when the worker sends data back to the main thread. Finally, we post a message to the worker to start the interchange of information. Creating and publishing ClojureScript libraries. To create a ClojureScript library, you'll need to set up a project, write the library code, and package it so that it can be distributed and used in other ClojureScript projects. In the code snippet, a ClojureScript namespace is defined with ns, and a simple function named add is declared, which takes 2 arguments and returns their sum. This could be part of a library that provides arithmetic operations, interop with WebAssembly. ClojureScript, being a hosted language that compiles to JavaScript, can interoperate with WebAssembly WASM modules. This enables ClojureScript applications to leverage performance-critical code written in languages like C, C++, and Rust, which compile to WASM. The general process involves loading the WASM module using JavaScript's APIs, and then calling into the WASM functions from ClojureScript, as you would with any external JavaScript library. The code snippet defines 2 functions for using WebAssembly in ClojureScript. Load WASMmat module takes a URL to fetch a WASM module and uses JavaScript's fetch and WebAssembly.instantiate streaming to load and instantiate the module asynchronously. The then chain extracts the instance object from the result. Use WASM module takes an instance of a WASM module, accesses the exports object which contains the functions and values exported from the WASM module, and demonstrates how to retrieve a function named myFunction from the exports. Mobile development with React Native and ClojureScript. Combining ClojureScript with React Native allows for the development of mobile applications using a modern, functional language while leveraging React's powerful ecosystem. ClojureScript compiles to JavaScript, enabling it to work with React Native seamlessly. This code snippet defines a ClojureScript namespace for a mobile app that uses Reagent, a minimalistic React wrapper, to create UI components for React Native. The AppRoot function defines a component with a text element, styled to center the text in the view. The init function triggers rendering of the AppRoot component into the app element, which is a typical entry point in a React Native application. Notably, the code demonstrates the harmonious interplay between ClojureScript's syntax and React Native's component structure, allowing us to define styles and properties in a succinct, expressive manner.